So thus far, we've learned about the stress intensity factor, a parameter that remains finite when stress is infinite near a crack. Now let's learn how we can use that parameter to predict fracture in a structure, where if that parameter, the stress intensity factor K, exceeds or is equal to a critical value, then fracture will occur in our structure. Well, that critical value of our structure is a material property, which we call the fracture toughness of our material. And both of the case of the calculation of the stress intensity factor and the property of K1C, the units are either megapascal times the square root of meters or KSI times the square root of inches. Now, with this criterion in place, for any particular geometry, we can calculate the K1, and then for a given material that we're studying, we can look up its material property and determine if fracture occurs. Now, if we want to incorporate safety into our design of our component, we can then develop this design criterion, wherein our design safety factor is equal to K1C, our material property, divided by our calculated stress intensity factor, where if N is less than or equal to 1, fracture occurs. And where if N is greater than 1, then we have a little bit additional design safety. Now, how do we obtain that material property of fracture toughness, that K1C parameter? Well, there exists a standard test method by ASTM International. It's a standards organization. Their E399 standard defines how we find the plane strain fracture toughness property of metallic materials. Within that standard, there exist several standard geometries which can be used under different loading conditions. The three most common geometries are the compact tension geometry, which is pretty efficient in dimensions, but requires some careful machining. There's the single edge notch bend sample, which is a little bit larger, may have a larger volume, but is very simple in machining. And then there's the semicircular notched sample, which is for more like rod cases of geometries. Now, with these standards, we'll take a sample of material, we'll carefully machine it into these shapes, and then we'll take that sample and we will cycle the sample. So we'll apply a cyclic load below the yield strip to kind of grow a very sharp crack in the structure. And then we will increase load. So we can do a load control or displacement control until fracture occurs in our part. It actually fractures until load drops to 0. And from that test, we can then calculate from that max load, the max force, and the test, what the fracture toughness was of a material. Now, more details and a cool video about how that process works is found in the supplemental playlist for this video series. So now that we know how to get to the fracture properties, the fracture toughness property, well, what does the property look like? Well, fracture toughness, that material property depends on, of course, the material itself. It can depend on the cracking mode, if it's mode 1, 2, or 3. It greatly depends on how we process the material. Did we heat treat it or age it? Did we hip it to change the microstructure, which leads to performance? It can depend on things like temperature. Are we fracturing in cryogenic temperatures where the material is expected to be more brittle, or at high temperatures where material is expected to be more ductile? Loading rate can play a case, slow loading or fast loading. And then also the state of stress at the crack. The crack is at an angle, the state of stress can be complex. For some simple engineering materials, we can say for engineering metals, Fracture toughness ranges from 20 to 200 megapascal times the square root of meters, depending on the class of alloy. While for polymers and ceramics, they have very low fracture toughnesses from 1 to about 5 megapascals times the square root of meters. If we go into like kind of specific classes of metals, we can see that there's pretty disparate ranges of properties. We can see in the steels, it can range from 14 to 99, depending on the type of steel. For titanium, from 15 to 115. So what that means is, depending on the chemistry, the exact chemistry of your alloy and its subsequent microstructure, you can get very different properties for fracture toughness, but also some different results in terms of the tensile properties of your material. Now, finally, a great way to look at this or to look at that effect is in terms of heat treatment. When we heat treat a material, it changes the microstructure of our material. Whether it's through aging or quenching or annealing, that change in microstructure changes the properties. It changes both the tensile properties and the fracture resistance. So for example, say we have a 4340 steel and we do different types of heat treatments. Well, the yield strength, if over a range of different heat treatments can range from 800 to 1600 megapascal. So the yield strength can double, while at the same time, fracture toughness can decrease from 190 to 40 megapascal times square meters. So that's a big change in toughness. In general, in materials, there's an inverse relationship between the yield strength of material and its fracture toughness. So as yield strength goes up, fracture toughness goes down. And with that, we have what we need in order to start solving fracture mechanics problems.